Now we will proceed to discuss the relativistic Doppler effect or Doppler effect in light by deriving a generalized expression for any arbitrary angle theta between the line joining the source and the observer and the direction of motion. Because in the previous cases we discussed three cases in which one is transverse Doppler effect, the angle is theta happens to be 90 degrees, and then two cases in longitudinal Doppler effect where the angles were 0 degree and 180 degree for recession case and approach case. But now we have taken an arbitrary angle theta between the line direction of motion of the source or the observer and the line connecting the two, right? So we have taken a interesting example here. An astronaut traveling in a spaceship, let us say, is sending a signal to a ground based observer who receives it using a receiver, and two successive signals he sends separated by a time interval of the, let us say he sends the first signal at a time t1 with respect to the ground observer. This t1 is measured by the ground observer, and t2 is the time at which the next signal is sent as observed by the ground observer. So both t1 and t2, first we have to be clear about it. We have to understand that both t1 and t2 are the times measured by the ground observer for the signals sent by the astronaut in the spaceship. Now this astronaut is traveling at relativistic velocity of v in a particular direction, and this direction of motion is making an angle theta with respect to the direction in which the signal is sent. So for any arbitrary angle theta, we are going to derive the expression, generalized expression for relativistic Doppler effect in light, right? Now what about the time at which the signal is received? Because the signal has to travel some distance from the source, which is in the spaceship, to the receiver here. It has to travel, so it is traveling with a velocity c, because it is a light signal. It will travel at a velocity c. It is going to travel with a velocity c, so it is going to take a definite time. And the time at which ground observer receives the first signal is t1 superscript is r, received t1 r, and for the second signal the time is t2 r, right? Now these are the times measured by the ground observer when he receives the signal. So he is able to see that this is just a hypothetical case. He is able to see the spaceship sending the signal, so he is noting down the time as t1. He is receiving the first signal at t1 r, and similarly t2 and t2 r is the case. Now this particular part is explained here, where this angle is theta, velocity of motion of the spaceship is v, and the time difference between t1 and t2 is del t. So the distance the spaceship moves in the time in which it sends two successive signals is v del t, and therefore it is making this vector v del t is making an angle theta in this particular direction. So this particular portion between this point and this point, from the source to this particular point, is here written as v del t cos theta. So the first signal has to travel an extra distance of v del t cos theta compared to the second signal, because if you drop a perpendicular from the point where the second signal is emitted to this particular line connecting this first signal with this source, you get the extra distance as v del t cos theta, because the angle here made is theta, and L is the general distance traveled by the signal from here to the receiver, and the second signal also travels the same distance L. So this particular distance is the extra distance that, due to the geometry of the problem, the first signal has to take some extra time to reach the ground observer. Now one may wonder, see, for this is valid only for very far away distances between the source and the receiver. The distance between the source and the receiver has got to be very far, because you can imagine standing on the earth and seeing, for example, a source of light moving which is very far away from you. Then these angles could be valid, because say for the same antenna, this motion will cause the signal to be received at the same spot here, but here some distance has been covered by the spaceship, and therefore there has got to be some change in the time, right? So that is what we. Similarly, these two times also differ. Let us call that del t over r here, superscript r, and that is t2 r minus t1 r, right? These are the times. Now if there are two successive signals or flashes of a particular source, that means it is two successive or consecutive waves emitted by this particular source, and therefore one can say that this del t must be linked to the frequency of the source as well, because this is like time period. Number of waves per second is the time period, and if two successive waves are emitted separated by a time duration, that happens to be the time period for this particular source of wave, right? And therefore with this understanding we will now try to proceed to derive the expression for the observed frequency of this particular source by the ground based observer with respect to the actual frequency emitted by the source, right? Now we can say that the time t1r at which the first signal is received by the ground observer must be equal to the time t1 at which the signal was sent plus the time taken for the signal to travel this distance, L plus V del t cos theta. This is this particular distance, extra distance, right? So therefore this time is t1 plus L plus V del t cos theta over c, because c is the speed at which this light signal will travel. So the distance over velocity is going to be a time, right? So that is the time. Similarly, for the second signal t2r is going to be equal to t2 plus, here the distance is only L, no extra distance here, so it is just L over c, right? Now we can subtract these two expressions to get t2r minus t1r is equal to t2 minus t1, and then this term will be the extra term because L over c is common here both, so that will cancel. So minus V del t cos theta over c, this is the extra term. Here we have this one already, we have taken it to be del t over r, which is equal to del t minus V del t cos theta over c. Now del t is common, so I take it out. 1 minus V cos theta over c is an extra factor that I am getting here, right? Now this is the time as measured by the ground observer, so it is called as the actual time. But in the spaceship, the time duration between two signals is going to be a proper time. So please check out my video on time dilation in special relativity if you don't know what is proper time. So therefore this time is actually a dilated time as measured by the ground based observer, so you cannot measure the actual time. What you would measure is a dilated time, so this time has got to be modified by the proper time. Let us call that as del tau with the relativistic factor 1 minus v squared over c squared within square root, dividing it, and this time signal is the time for him, so it is not going to be dilated. It is actual time, proper time for him, and this is proper time for the spaceship. So del tau is a proper time for the spaceship, del t is that time measured by the ground based observer, and del t to the power r is the proper time for the ground based observer for his measurement of the signal as he receives it. So the rest of the terms is going to remain the same. Now this particular time del tau in the frame of reference of the spaceship is linked to the frequency of the wave in that particular frame of reference. So it is the reciprocal of the actual frequency of the source, and this del t r, if the two waves are consecutive waves, the duration will be connected to the frequency as measured by the ground based observer. So I am going to call that del t power r as the frequency, that is measured frequency, and del tau is the actual frequency of the source. So we are going to continue writing this as, in terms of frequency, 1 over nu is equal to 1 over nu naught multiplied by square root of 1 minus v squared over c squared, and in the numerator we continue to have the 1 minus v cos theta by c term. Now if we revert it, we would be getting expression for frequency, which is nu is equal to nu naught multiplied by 1 minus v squared over c squared over 1 minus v cos theta by c. Now this is the expression, generalized expression for relativistic Doppler effect for any arbitrary angle between the direction of relative motion of the source and the observer, and the line joining the source to the observer. This is the most general expression for a relativistic Doppler effect or a Doppler effect in light. Right, now we can proceed to show that the three cases that we discussed earlier, namely the transverse Doppler effect, the longitudinal Doppler effect approach case, and the longitudinal Doppler effect the recession case, all these three cases that we discussed separately earlier, they turn out to be special cases of this general case. This general expression should lead us to those three results again. So let us just verify that now. First case is the transverse Doppler effect, where this theta, the angle, is going to be taken to be 90 degrees. So theta is equal to 90 degrees. If you substitute in this equation, cos 90 is going to be 0. So this term vanishes, the entire denominator is now 1, and therefore you get nu is equal to nu naught square root of 1 minus v squared over c squared, and this expression is the same that we derived for the transverse Doppler effect earlier. Right. So for the longitudinal Doppler effect, for the approach case, the line connecting the source to the observer and the velocity, they are in the same direction because it is longitudinal, they are parallel to each other, and therefore the angle here is 0 degree. So here theta is going to be 0. If you substitute cos 0, it's 1. So in the denominator you are getting 1 minus v over c. So I will continue the steps here. Nu is equal to nu naught square root of 1 minus v squared over c squared. In the denominator I will have 1 minus v over c. And the numerator I will again write it as nu naught 1 plus v over c, 1 minus v over c. Denominator I will have square root of 1 minus v over c, square root of 1 minus v over c again, and therefore these two terms will cancel, resulting in the expression for longitudinal effect Doppler effect approach case, that is nu is equal to nu naught square root of 1 plus V over C divided by 1 minus V over C, which is the same as the one that we discussed earlier. Same expression has been derived as a special case of the general case now. And finally, we can again verify whether we are getting the same expression for recession also. In this particular case, the directions are going to be 180 degree angle. So therefore, it is recession. So we have theta as 180 degrees now, and therefore if you put cos 180 degree here, cos 180 degrees minus 1. So if you substitute minus 1 here, the denominator becomes 1 plus V by C. So here I'm going to modify here. So I will put here 1 plus V by C for the recession case now, and therefore the numerator is same, the denominator you have two 1 plus terms, and therefore now you will cancel the 1 plus with this 1 1, and therefore the denominator you will have 1 plus, numerator you will have 1 minus. So finally you will have the expression here as nu is equal to nu naught square root of 1 minus and plus. So 1 minus V over C divided by 1 plus V over C, and this is the final expression for the longitudinal Doppler effect for the case of recession in relative motion between the source and the observer, which we had derived earlier as a particular case, but now it turns out to be a special case of the general case expression. Thus, in this video, we have been able to derive all the expressions for Doppler effect in light or the relativistic Doppler effect using the principles of special theory of relativity. One of the interesting applications of Doppler effect in light or the relativistic Doppler effect is in binary stars. By observing the spectrum of binary stars, one can understand the configuration of the binary system, and the spectrum of the binary stars is either red shifted or blue shifted. Depending on whether the spectrum of the binary stars is red shifted or blue shifted, one can understand whether the member of the binary system is approaching us or receding with respect to the Earth. We will discuss the relativistic Doppler effect in binary stars as a separate video. Please do check out for that video as well if you are interested. Thank you.